am Mr. P. Mabu Hussain, Assistant Professor of EEE from Institute of Aeronautical Engineering, Hyderabad. Today, in this video, we are going to discuss about the capacitance of single circuit and double circuit three-phase transmission line. So, if you observe the learning outcomes of this lecture, by the end of this lecture, the students will be able to understand what is the single circuit transmission line as well as what is the double circuit transmission line. And he also know the expression of capacitance for a single phase three-phase transmission line, and also develop the expression for capacitance of a three-phase line if it is having a bundled conductor configuration, and also develop the expression for a double circuit three-phase transmission line. So first let us see what is a single circuit and what is a double circuit three-phase transmission line. Right, this is already we discussed while discussing about the inductance. So but again just recall this. Okay, in a single circuit transmission line, you will be having only one set of three-phase conductors. So three-phase conductors may be represented with, so let us A, B, C, or sometimes they may be represented with the numbers 1, 2, 3. Sometimes they may be represented with R, Y, B phases. Right. So if you observe a single circuit three-phase transmission line system, so in such a case you will be having only one set of these three conductors. So this may be either ABC, 1, 2, 3 or R by B. Only one set of conductors will be there in a single circuit three-phase transmission line system. Right. According to the voltage level, there may be one single earth or two earth conductors also will be there. Suppose if you observe the first figure here, so this is a single circuit three-phase transmission line with a single earth wire. So this earth wire is to protect the transmission line system from the lightning strokes. So generally, this earth wire will be top of the tower. So at the tip of the tower, you will be having the earth wire. Okay. So now here the three phase lines. So whether it may be ABC 1, 2, 3 or R by B. So those will be connected with some insulators here. Okay. So now here only one set of the three phases will be there. This is maybe A, B, C. Okay. Only one set of three phase conductors are there. So this transmission line system is a single circuit transmission line, and here earth wire is only one. So this is a single earth wire transmission line. Okay. So if you observe the double earth wire transmission line, here you will be having the tower structure like this, and in which you will be having two earth wires. Right here in this transmission line system also you will be having only one set of three phase conductors. Here those may be represented with 1, 2, 3 conductors, or maybe R by B also. Okay. So this is about the single circuit three phase transmission line. So in case of double circuit transmission line, you will be having two sets of three phases. Okay. So one set may be ABC, another set may be A dash, B dash, C dash. So like that, two sets of three phases will be there in a double circuit three phase transmission line. So if you observe the first diagram here, so now if you observe this diagram here, at left side you will be having one set of three phases. On the other side you will be having another set of three phases which are represented with A dash, B dash, C dash like this. So this is one set and this is another set. So this type of transmission line is called a double circuit three phase transmission line. Okay, right? Here the earth wires, if you observe, you will be having only one single earth wire here in the this type of transmission line system. So now if you observe this figure here, here you will be having left side one set of three phase conductors, and the right side you will be having another set as 1 dash, 2 dash, 3 dash. Right? So this is one set, this is another set. So this is a double circuit transmission line, and the tower structure it is having two earth wires here. Okay, this is about the single circuit transmission line as well as a double circuit three phase transmission line. Okay. Now till now we discussed about the capacitance of three phase transmission line by considering symmetrical configuration as well as unsymmetrical configuration in the previous videos. So those transmission lines which are three phase transmission line by considering only one single conductor in each phase. So those will be coming under the single circuit transmission line system. Okay. And the capacitance, if you see here, so the capacitance of a single circuit asymmetrical three phase line. Right. So single circuit here we are representing. So that means in a single circuit transmission line you will be having three conductors. Okay. Now if you observe the distance between any two, so let it be conductor 1 conductor 2, conductor 3, and distance is, between 1 and 3 is D13 or D31 also you can say, and between distance between 1 and 2 will be D12 or D21. So distance between 2, 3 is D23, right? So this may be represented 3, 1 also. Okay. So now if you observe all the distance, if all the distances are same, you can call it as a symmetrical three-phase transmission line. If the distances are not same, then it is called a asymmetrical three-phase transmission line. Now, for this asymmetrical three-phase transmission line system, we derived the capacitance equation in the previous videos, right? So the capacitance of single circuit asymmetrical three-phase line, the value is CAN. CAN is the per phase capacitance. So this value will be equal to QA by VAN, and the VAN value you got here. Okay. So the CAN value here is 2 pi epsilon naught by ln dq by r. So the units are farads per meter, right? So you can use this expression for calculating the capacitance of a single circuit asymmetrical three-phase transmission line. And here R is the radius of each conductor, and D equivalent here is the D12, D23, D31 whole to the power of 1 by 3. So which is called the equivalent equilateral spacing, right? So you can use this equation for calculating the per phase capacitance of a single circuit asymmetrical three-phase line, or you can even use this equation also, and this equation also is derived from this equation only. Okay, CAN is equal to 0.0242 by log D equivalent by R. So microfarads per kilometer here. Okay, so you can use either of the equation for calculating the capacitance, right? So in case of a symmetrical transmission line, so the distance between any two conductors is same, so which is represented with D. So that means here D12, D23, D31 all will be equal to D. So the expression for D equivalent, so D equivalent is equal to D into D into D into whole to the power of 1 by 3, which will be equal to D. So D equivalent will get equal to D. So the capacitance equation for equilateral spacing, or you can even say that the line is a symmetrical three-phase line. Okay, the capacitance of single circuit three-phase symmetrical line will be CAN is equal to 0.0242 by log D by R. So which is in microfarad per kilometer. Suppose if you use this equation, so then the same expression can be written as CAN is equal to 2 pi epsilon naught by ln D by R. So units will be farads per meter. Okay, so you can use either this equation or this equation for calculating the capacitance of a single circuit three-phase transmission line with the symmetrical spacing. Okay, so the derivation for these symmetrical and asymmetrical transmission lines we already derived in the previous videos. Once you go through the previous videos, you can know how you get these equations. Okay, right. So now let us derive the expression for calculating the capacitance of a bundled conductors three-phase transmission line. Right, as I said before, a three-phase transmission line, if it is a single circuit transmission line, you will be having one set of three phases. Right, one set of three phases like that it may be there. Okay, whether it is a symmetrical line or asymmetrical line. So you will be having three phases. Those may be represented with A, B, C, three-phase conductors. Now, suppose if each conductor is having a bundled conductor configuration, so then the transmission line is called a bundled conductor three-phase transmission line. Right? If you are having one set of one set of three phases, then that will become a single circuit bundled conductor configuration three-phase transmission line. Okay. So now for calculating the capacitance of this bundled conductor three-phase transmission line, so the expression will be the same. So CAN is equal to 0.0242 by log D equivalent by DS, which is in microfarad per kilometer, or 2 pi epsilon naught by ln D equivalent by DS farads per meter. So any one of these two equations you can use for calculating the capacitance of a three-phase line. Okay. So now here in the three-phase line, instead of taking one single conductor per each phase, you may be taking bundled conductor. So this bundled conductor will be having two conductors per phase, or three conductors per phase, or four conductors per phase configuration. Okay. So this total will be one conductor only. Okay. So if you take a three-phase transmission line with a bundled conductor configuration, and that is two bundled conductors configuration, so then that line will be represented like this. So A will be having 2 conductors, B is also having 2 conductors, and C is also having 2 conductors like this. So this is A phase, B phase, and C phase. Each phase will be having 2 bundled 2 conductors, right? So this configuration is called the bundled conductors configuration, in which the bundled conductor will be having 2 conductors for each phase. In some cases, you may be having 3 conductors for each phase also. So like this. So now this configuration is called the 3 conductor configuration of bundled conductors. Sometimes you may be even having the 4 conductors also. So the 4 conductors, those will be represented like this, like a square. So now A phase, B phase, and C phase. Each phase will be having the 4 subconductors, right? Now this each phase you can call it as a bundled conductor. Okay, so the first one here is a 2 conductor bundled configuration, and in the second case it is a 3 conductors bundled configuration, and in the third case it is a 4 conductors bundled configuration, right? We will take the each case and we will derive the expression of capacitance for each phase, each case. Okay, for any case the formula for calculating the capacitance will be the same. Can is equal to 0.0242 by log D equivalent by ds microfarad per kilometer, or 2 pi epsilon naught by ln D equivalent by ds farads per meter. Okay, right, now here D equivalent is nothing but equivalent equilateral spacing, and that D equivalent you can use this formula for calculating the D equivalent. So D equivalent is equal to D12, D23, D31 whole to the power of 1 by 3. And D12 here is nothing but distance between conductors 1 and 2. Instead of representing these 3 phase conductors as ABC, they may be represented 1, 2, 3. So now the distance between 1 and 2 is called the D12. The distance between 2 and 3 is called the D23. Distance between 3 and 1 is the D31. Okay, so for any case, so in all the 3 cases, the calculation of D equivalent formula will be the same. D equivalent is equal to D12, D23, D31 whole to the power of 1 by 2 for all the 3 cases. Now, how we can calculate the DS? Say DS is called the self GMD, and for calculating the self GMD, you have to follow different procedure for each cases. Okay, we will do the procedure for calculating the self GMD for each configuration. Okay, so now for asymmetrical transposed line, D equivalent will be D12, D23, D31 whole to the power of 1 by 3, and if it is a symmetrical transposed line, so then D12, D23, D31 will be equal to D. So this D equivalent you can write it as D only. Okay, D is here is the number distance between any 2 lines. So this will be the same for symmetrical transposed line. Okay, I think you got how to calculate the D equivalent for any case. The D equivalent for any case you can calculate by using this expression. Now, how you can calculate the DS for different configurations? Okay, suppose if you take a 2 conductor bundled configuration, in which 2 conductors will be there for each phase. Okay, so first conductor, second conductor, and third conductor. So each will be having 2 conductors. So those are represented here, and the distance between those 2 subconductors it is given as small d. Okay, so let us call each phase is having a 1 conductor, and that conductor is having 2 subconductors like that. You assume. Okay, now the distance between these 2 conductors inside the conductors, that is given as d here. Now for this you need to find out the self GMD, right? So now the value of self GMD ds will be equal to, now here for calculating this self GMD you have to take all the possible distances by considering the self distance also. Okay, suppose if this subconductor, if you represent this as A and this subconductor as B, so then all the self distance, if you take conductor A, subconductor A here, so then the distance, self distance is DAA, and another distance is DA to B. So this is one set, and another set will be if you take the conductor B here, so then DBB and DB to A. So this whole to the power of 1 by, so how many subconductors are there? There are 2 subconductors, so 2 square you have to consider. Okay, so this will be equal to DAA, DAB D BB D BA whole to the power of 1 by 4 you will get. Okay, and the self distance DAA and DBB, so both will be equal to radius of the conductor in case the capacitance is capacitance. If you want the inductance, that will become R dash. Okay, so as we are as here we are determining the capacitance DAB and DBB, this value will be equal to R. Okay, and DAB distance here is nothing but DAB distance is small d. So if you substitute this here in this expression, so DA is R, DAB is small d, DBB is again R, DBA is again D whole to the power of 1 by 4. So this can be written as R square D square whole to the power of 1 by 4. So which is equal to RD whole square whole to the power of 1 by 4, and 2 2s I will get. So this will be equal to RD whole to the power of 1 by 2. So this is the value of DS, which is the self GMD in case of a two conductor bundled conductor. Okay, two conductor configuration of bundled conductors. Okay, so DS is equal to R into D whole to the power of 1 by 2. Okay, so in similar way, if you take a three conductor bundle, okay, so if you observe the each phase, so if you have the phase 1, so the phase 1 will be having three subconductors. Phase B, phase 2 is also having three subconductors. Okay, and phase C is also having phase 3 also having three subconductors. Now 1, 2, 3 are the three conductor bundled configuration. Here these three, so these three are arranged like a triangle like this. Okay, and the distance between any two conductor is kept it as same, which is equal to small d here. Okay, and also you call them this as A, P, C here. Now you calculate the self GMD. Self GMD is equal to, here also you have to take all possible products here. Suppose if you take the phase phase A, okay, or phase subconductor A here, so then self distance DAA you will get. Now A to B and A to C, two distances you will get. DAB is another distance, DAC is another distance. Okay, so now if you take the conductor subconductor B here, so then DBB self distance, DB to A, DB to C. Okay, then if you take the conductor C, DCC, DCA, DCB, you have whole to the power of 1 by how many subconductors are there? There are three subconductors, so 3 square you will get. Okay, again here also the self distances DAA, DBB and DCC. So this value will be equal to radius of the conductors, right? So if you substitute here, so DAA is R and DAB distance is small d here. So if you observe any distance DAB, DBC, DCA, so all the distance is small d only. So DAB is small d, DAC is also small d. So then DBB is again R, DBA is small d, DBC is small d, DCC is smaller, DCA is D, DCAB is D. Whole to the power of 1 by 3 square will be 1 by 9. Okay, so now this can be written as RDD whole cube whole to the power of 1 by 9. Okay, so now 3 3s are it will get. So this can be written as R into D square whole to the power of 1 by 3. So this is the value of self GMD in case of a three conductor configuration of bundled conductors, right? The value of DS is R into D square whole to the power of 1 by 3. So this is how you can determine the self GMD for a three conductor arrangement of a bundled conductor. Okay, so now you can even have the four conductors bundled configuration also. So which means that each phase is having four conductors which are arranged like a square here. So this is one phase and this is another phase and this is another phase, right? In each phase you will be having four subconductors which are arranged like a square. Okay, so if you observe here, this is a square. The distance between any two conductors is represented with small d here. Okay, so you assume that the subconductors are represented A, B, C, D. Okay. Now the distance from B to C, if you observe, this value will be equal to, so now if you take this right angle triangle, this will be D square plus D square, so which will be equal to root 2 into D you will get. Okay. So now you will, this distance from A to D also the same, root 2 into D. So now the value of ds, how you can determine? So you have to again write the product of all the distances by considering each subconductor. Okay, if you consider the subconductor A, the distances are DAA, DAB, DAC, DAD, whole to the power of. So this is one product, one set of product. If you consider the subconductor A, so if you consider subconductor B, then DBB, DBA, DBC, DBD. If you consider the conductor C, DCC, DCA, DCB, DCD into, if you consider conductor D, DDD, DDA, DDB, DDC, whole to the power of 1 by, so here in this 4 subconductors are there, so 4 square you have to consider. Okay, so again the value of DAA is same as DBB, is same as DCC, is same as DDD, which is equal to radius of the each subconductor. Now you write the value of all the distances and substitute here. So DAA here is smaller, DAB, A to B distance is small d, A to C distance is also small d. So A to D if you observe, so this A to D distance is this distance which is root 2d. Okay, so this is one product. So then DBB is R and DBA, BA is D, DBC if you observe, this BC is root 2 into D, DBD is again D. Okay, so then DCC is R, DCA is D, DCB is root 2D, DCD is D. Okay, so then DDD is R, DDA is D, DA here is root 2D, sorry, root 2D. So DB here is D, DC here is also D, whole to the power of, this 1 by 4 square is nothing but 1 by 16. Okay, so now if you observe all the terms are the same. So whose value will be R into root 2 into D cubed, right? So whole to the power of 4 you will get whole to the power of 1 by 16. So this is the value of ds. So this again 4 you will get, and this value will be equal to root 2 into R into D cubed whole to the power of 1 by 4. So this is the value of ds in case of a 4 conductors bundled conductor. Okay, so this is how you can determine the self GMD for different bundled conductor configuration. Okay, so for 2 conductor bundle you are getting ds is equal to RD whole to the power of 1 by 2, and for 3 conductor bundle you are getting ds is equal to R into D square into 1 by 3, and for 4 conductor bundle you are getting ds is equal to root 2 into R D cubed whole to the power of 1 by 4. Okay, so but the D equivalent will be the same, so which is equal to D12, D23, D31 whole to the power of 1 by 3. So in case of a asymmetrical line, and in case of symmetrical line this will become equal to capital D only, so which is the distance between any 2 types of line, right? So once you know the D equivalent and ds for any configuration of bundled conductor, so then you can use this formula for calculating the value of capacitance, okay, which is a per phase capacitance. CAN is equal to 0.0242 by log D equivalent by ds, which is in microfarads per kilometer. So or you can even use CAN is equal to 2 pi epsilon naught by log D equivalent by ds, which is in farads per meter. Okay, right. So now let us see the capacitance of a 3-phase double circuit transmission line. Okay, in a 3-phase double circuit transmission line you will be having 2 sets of 3 phases. Okay, so one set will be represented with A, B, C, another set may be represented with A dash, B dash, C dash in opposite direction. So this arrangement will make the conductor capacitance to be increased. Okay. So now this is one set of configuration. This is another set of configuration. Right. Now after transposing all the three conductors, you will get this type of configuration. Right. So transposition is nothing but all the conductors will occupy the original position of every other conductors in equal intervals of distance. Okay. So like that, right? So this is L by 3 distance, this is L by 3 distance, L by 3. This is first section, second section, and third section. Okay. So in each section, you will be having two sets of three phases in case of a double circuit three-phase transmission line. Right? If you observe the first section here, so then ABC conductors are there in opposite direction. A dash, B dash, C dash conductors will be there in one section. So then, if you go to the second section, ABC positions will change. Right? Accordingly, C dash, A dash, B dash positions also will change. If you take the third section, again the position of ABC will change, and accordingly, other phase also will change. Okay. So this is the arrangement of three-phase double circuit transmission line after transposition. Okay. So for this case also, for calculating the capacitance, the equation is the same. CAN is equal to 0.0242 by log D equivalent by DS, which is in microfarad per kilometer, or 2 pi epsilon naught by ln D equivalent by DS in farad per meter. Okay. So this equation is same for any type of three-phase transmission line. Okay. Now, how we can calculate the value of D equivalent and DS in this case of transmission line, which is the double circuit three-phase transmission line. In case of double circuit three-phase transmission line, the value of D equivalent you can calculate by using this expression. D equivalent is equal to DAB, DBC, DCA whole to the power of 1 by 3. Now here, what is the value of DAB and what is the value of DBC and what is the value of DCA? Now here, this DAB is nothing but, so this is the mutual GMD by considering phases A and B. Okay. So DAB is mutual GMD by considering the phase A and B. And DBC is the mutual GMD by considering phase B and C. And DCA is the mutual GMD by considering phase C and A. Now the total equivalent GMD or equivalent self GMD also you can say, this value will be equal to DAB into DBC into DCA whole to the power of 1 by 3. Okay. So now here the value of D equivalent is same as the DM. So DM is the mutual GMD also you can say. Okay. And DS here is, you can calculate by using this expression. So DS is equal to DSA, DSB, DSC whole to the power of 1 by 3. Now again here DSA is self GMD by considering phase phase A. DSB is the self GMD by considering phase B. DSC is the self GMD by considering phase C. Okay. How you can determine this DAB, DBC, DCE so that you will get D equivalent? How you can determine DSA, DSB, DSC so that you will get a DS by using this expression? We will see. First, let us calculate the value of DAB, DBC, DCA. Okay. So DAB, DBC and DCA all are the mutual GMDs. Okay. So first one, DAB is the mutual GMD by considering phases A and B. Right. Now if you consider the phases A and B, so each phase will be having two subconductors. One is A, another one is A dash. So if you consider B, you have the B and B dash. Okay. So A dash, B dash. Now you have to write the product of all the mutual distances. Now if you consider A here, from A, the mutual distance will be D, AB is one distance, then A, B dash is another distance. So DAB is the distance from A to B, DAB dash is another mutual distance. So now if you consider A dash B is one mutual distance, A dash B dash is another mutual distance. So D A dash B dash, D A dash B whole to the power of 1 by, so now here how many conductors are there? Here how many conductors are there? So this will be 2, this will be 2. So 1 by Mn you have to consider, which is 1 by 2 into 2. So which is nothing but 1 by 4. So here 1 by 4 you will get. Okay. So now here after transposition here in the diagram and in section 1 we are assuming that the distance between A and B is capital D and distance between B and C is capital D and distance between A to C dash is D1, A to D2 is V dash, so A to B dash is D2, A to A dash is D3 like, and B to B dash is D4 and A to C is D5 like that we are assumed here. Okay, so now based upon our assumptions, you have to derive the equations here. Okay, so DAB. So what is the distance from distance DAB? So DAB here is in section 1, that value is capital D here. Okay, so DAB is capital D. So that value we are considering here. So then DA to B dash, if you observe A to B dash, this distance is D2. So here we have taken D2 and D2 D A dash to B dash. So A dash to B dash, this distance here. So this distance is same as this distance, which is capital D again. So D A dash to B. So D A dash to B here is nothing but, so A dash is here you are having A dash to B. So this distance here and this distance is same as this distance, which is D2 again. Okay. So now here this equation can be written as D into D2 whole square whole to the power of 1 by 4 and 2 will get cancelled. So you will get D D2 whole to the power of 1 by 2. Okay. So this is about the DAB. So which is mutual GMD by considering the only phases A and B. So then next DBC. Okay. So DBC is the mutual GMD in section 1 by considering only phases B and C. Okay. So B and C. So B is having B dash, B dash. So B is having B dash and C is having C dash. Now you have to consider all the mutual distances. So now if you consider B to C is one mutual distance, B to C dash is another mutual distance. That product you have to consider. DBC, DBC dash. Now if you take B dash to C and B dash to C dash, it is another mutual distances. So that product also you have to consider. B dash to C dash, B dash to C. Whole to the power of, so here also 2 are there. So 1 by 2 into 2, 1 by 4 you will get here again. Okay. Now again, what is the DBC distance? Okay. So DBC distance, if you observe here, so DBC, so this distance, which is capital D, we have written here, and B to C dash. So B to C dash is, so this distance. Okay. So that this distance is same as this distance, which is again D2 here, and B dash to C dash if you observe. So B dash to C dash, B dash to C dash is this distance. So this distance is same as this distance, which is capital D, and B dash to C. So B dash to C here is this distance. Okay. So this distance again it is same as the D2 only. Okay. So after writing this, again you will be having D into D2 whole to the power of 1 by 2. So now if you observe DAB and DBC, the value will be both are same. Okay. So then DCA. So DCA here you have to calculate by considering the phases C and A. C is having C dash, A is having A dash. Now all the mutual distances you have to take the product. So DCA, DCA dash, DC dash, A dash, C dash, A whole to the power of 1 by 4 again here also you will get. Now what is the DCA, DCA dash, DC dash, A dash, DC dash, A? Those values you have to observe from this diagram. So then if you observe and if you write the values, you will get DCA is equal to D5, DCA dash is D1, DC dash A dash is D5, DC dash A is D1 here. Okay. So this value will be equal to D1 D5 whole to the power of 1 by 2 you will get. Okay. So now you got all the values DAB, DBC, DCA. So which are the mutual GMD by considering two phases at a time. So the value of total mutual GMD of double circuit transmission line. So which is capital DM will be equal to D equivalent. So that value is DAB, DBC, DCA whole to the power of 1 by 3. Okay, by using this expression you have to calculate, right? See here. So what is DAB? D into D2 whole to the power of 1 by 2. So that we have considered here. Then DBC, D into D2 whole to the power of 1 by 2. So DCA, D1, D5 whole to the power of 1 by 2 whole to the power of 1 by 3 you have considered here. So now here, if you observe D, D and so D, D. So here you have D, here you have D. So D square whole to the power of 1 by 2. Okay, then D2, here you have, here you have. So D2 square whole to the power of 1 by 2. So then D1 whole to the power of 1 by 2, D5 whole to the power of 1 by 2, whole to the power of 1 by 3 you will get. Okay, so here 2 will get cancelled, here also 2 will get cancelled. So then this value will be written as D into D2 into D1 whole to the power of 1 by 2, D5 whole to the power of 1 by 2, whole to the power of 1 by 3. So this equation you will get. Okay, so now if this 1 by 3 also spread to all these terms, so then D equivalent is equal to D power 1 by 3, D2 whole to the power of 1 by 3, D1 whole to the power of 1 by 6, D5 whole to the power of 1 by 6. This is about the D equivalent. Okay, so then you have to find out the DS. So DS is equal to DSA, DSB, DSC whole to the power of 1 by 3. Again here the value of DSA, DSB, DSC are the self GMD by considering each phase, phase A, phase B, phase C. Okay, so DSA here is the self GMD by considering phase A. Now phase A is having A and A dash conductors, right? Now you have to write the all the distances by considering these two. So if you consider A, the distance DAA, self distance also considered DAA, DAA dash. So if you consider A dash, DA dash, A dash, D A dash A whole to the power of 1 by, as here there are 2, 4 you will get. Okay, and DAA is R, DA dash A dash also R, and D2, DA to A dash distance. So from the diagram you have to write, right? A to A dash distance is D3 here. Okay, so this value is D3 whole to the power of 1 by 4. So if you calculate it, R into D3 whole to the power of 1 by 2 you will get. So this is about the DSA. Okay, so then DSB also you can calculate in a similar manner. So DSB is equal to, so you have to consider only phase B, B dash. So the products here will be DBB, D, B dash, D, B dash, D, B dash, B whole to the power of 1 by 4 you will get. Okay, so this BB and BB dash will be equal to R here, and B to B dash distance if you observe from the diagram here. So B to B dash distance, this distance, so which is D4, right? So D4 here you will get whole to the power of 1 by 4. So this value is equal to R into D4 whole to the power of 1 by 2 you will get. So this is about the DSB. Okay, similarly you can calculate the value of DSC also here by considering C and C dash. So the distances will be DCC, DCC dash. So if you consider C dash, C dash, C dash, C dash, C whole to the power of 1 by 2. So 1 by 4 this one. Okay, so DCC is R, and C to C dash distance if you observe, so this distance. Okay, so this distance will be equal to D3. See here. So D3 is this distance A to A dash, and A to A dash this distance, and C to C dash distance both will be same, which is equal to D3A. Okay, so this is D3, and C to C dash R, C dash C. This is again also D3 whole to the power of 1 by 4. Okay, this can be written as R D3 whole to the power of 1 by 2. So DAC you got equal to R into D3 whole to the power of 1 by 2. So the value of DS you can calculate now, right? The value of DS is equal to DSA into DSB into DSC whole to the power of 1 by 3. Okay, and the value of DSA here is R into D3 whole to the power of 1 by 2, that we have written here. The value of DSB is R into D4 whole to the power of 1 by 4, 1 by 2, here we have written. The value of DSC is R into D3 whole to the power of 1 by 2, that we have written here, whole to the power of 1 by 3. Okay, so now if you solve this, the value of DSC will get R into D3 into R power 1 by 2 into D4 R whole to the power of 1 by 2 whole to the power of 1 by 3. So now this 1 by 3 also is spread to inside this. So finally you will get this equation, R into 1 by 3, sorry, R power 1 by 3 into D3 whole to the power of 1 by 3, R into 1 by 6, R power 1 by 6, D4 power 1 by 6. Now here, if you write these two, so then that will become R into, sorry, R whole to the power of 1 by 2, D3 whole to the power of 1 by 3, D4 whole to the power of 1 by 6. So this is the final value of DS. Okay. So now you get the value of D equivalent, you got the value of DS. So then finally you can calculate the value of capacitance per phase. CAN is equal to 0.0242 by log D equivalent by DS. Okay. Here the value of D equivalent is this one, D power 1 by 3, D2 whole to the power 1 by 3, D1 whole to the power of 1 by 6, D5 whole to the power of 1 by 6. And the value of DS is R whole to the power of 1 by 2, D3 whole to the power of 1 by 3, D4 whole to the power of 1 by 6. So which is in microfarad per kilometer. And if you want farad per meter, so then CAN is equal to 2 pi epsilon naught ln D equivalent by DS you have to write. Okay. So once after knowing the capacitance per phase, you can even find out the charging current. Charging current is equal to voltage per phase by XC, and this can be written as V phase by XC is 1 by omega C, J omega C. So this can be written as J into omega C V phase here, right? So here this capacitance is nothing but per phase capacitance. You can write it as CAN V phase. Okay. So this omega here is nothing but 2 pi f. So this can be written as J 2 pi f CAN V phase. So like that you can calculate the charging current. Okay. So this is how you can determine the value of capacitance in case of your bundle conductor configuration as well as double circuit transmission line system. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.